Okay, now we're going to continue with part 2 of looking at rational functions. So we have the definition again there. So this is case 3. In this case, this rational function doesn't have a horizontal asymptote. It has another type of asymptote that is not horizontal. It has a vertical asymptote, but we're going to talk about that. This is actually called a slanted or oblique asymptote. So let's look at what it is that it does have. Let's start with the vertical asymptote. And basically, very simply, you set the denominator equal to 0. That's the easiest asymptote to get. That's your vertical asymptote. The horizontal asymptote doesn't exist. The reason it doesn't exist is because the numerator has a higher degree. That's the, if you look at the exponent, the degree of the term in the numerator, that's 2. All right. And this degree 2 is bigger than a degree of the denominator, the term in the denominator, which is 1. Okay, so that degree is 1. So what is happening is that you have basically 2 is greater than 1, or the degree of the denominator is smaller than the degree of the numerator. And whenever you have a situation like that, you will always going to get an oblique. Oblique is a Q asymptote, or you can say slanted. Asymptote. Okay, so but what is it that we want to get? Well, here is the equation. This is the process to get the equation of the oblique asymptote. You have to actually do the division, and you got to use a synthetic division, or you can use the long division. You know, for simplicity's sake, let's do the long division together. So here is the process. We are going to find the equation of the oblique asymptote using long division. All right, so we know how to do this. Now, to make it easier for you guys, let's write this properly. Actually, x squared plus 0x plus 0. So I'm including the linear term and a constant term, but I'm putting a 0 in there so that you can see the placement of it. If you remember the process of doing the synthetic division. All right, let's go through that. So basically, you want to get x squared, so that would be x times x squared, and that would give you x squared and then minus 4x. Now remember, you're subtracting, put them in a bracket, so that would be 0. That would be gone. And then minus negative 4x is just positive 4x, and we need to get the 4x, so we have to, so plus 4, because 4 times x is 4x, and 4 times minus 4 is minus 16, and sure enough, we are subtracting, that would be 0, and then we have positive 16 as the remainder. All right, now here is the deal. The quotient which is x plus 4 that is the equation of your oblique asymptote. So y equals to x plus 4 is the equation of the oblique asymptote. All right, that's how you get it. That's the process that is you get it. You have to use the division, long division, to do that, or synthetic division, doesn't matter. And then go ahead and then just graph it, really. But again, to graph this, we got to use Desmos. It just takes a long time to do a table of values. So let's go ahead to Desmos and graph. Okay, so let's go ahead and graph. By the way, this will end up being, because we have a vertical and the oblique asymptote, so this will end up being a discontinuous graph. Okay, discontinuous function. So let's go ahead, and here it is. So actually, I wanted to show you that first we punch in the equation, and then when we graph it, that's what we will get. Now, I purposely wrote the equation of the asymptote as well here, just so that you can see it, even though it's not dotted line and it's not supposed to show up, but I just want to make sure that's the blue line. You see that? So that is the equation of the the oblique asymptote. And remember, the only time you're going to get an oblique asymptote is when the degree of the denominator is less than the degree of the numerator. Whenever you have a setup like that, you will end up getting your oblique asymptote. And of course, what is the vertical asymptote? The vertical asymptote is right where you can see the top x equals to 4. That would be your vertical asymptote. All right, let's go and deal with the last case. Now, before we continue to case 4, I do have to make a point here. And the point is that whenever you have a setup like this, where the numerator has a higher degree, and then denominator has a lesser degree than the numerator, that only works if there is no way to simplify this rational expression. If you can simplify it, then that's a different type of a setup that you're going to get. That's your case 4, by the way. Okay, so not necessarily, I stand corrected, not necessarily every time that you have a higher degree term in the numerator than a denominator, you're going to get an oblique asymptote. The only way that will happen is that, first of all, it has to do with the degree of the polynomial function in the denominator, as well if it's factorable or not, or it can be simplified. So now let's move in, a good segue to move into case 4. So here is the perfect example of that. This graph will have neither asymptotes nor vertical. I mean, even though you think that it does, because the denominator you set it equal to 0 and you end up getting 2. But here's the thing, you can actually simplify this rational expression. So to simplify that, what do we have? This is the difference of the squares. Let's factor the numerator. Let's see what we can do. And notice that if I would have given you this as an example or a question of simplifying a rational expression, you could have just done that, factor the top, and then look at the common factor and you divide. You say, oh, okay, x minus 2 and x minus 2 is a factor. The final answer will end up being x plus 2. Well, in this case, it is. In this case, f of x, which is our function, is equal to x plus 2. But there is a catch. The catch is the non-permissible value that we have in this case, the denominator, x cannot be equal to 2. And if x cannot be equal to 2, therefore f of x or y value cannot be equal to 4. That is a crucial part. That means the coordinate 2, 4 is not on the graph. But every other point will work. Well, how is that going to look like? Well, this is a linear graph, x plus 2 equal to y. That's the mx plus b. That's just a line. It's a linear function. Let's graph that, and you can do that actually freestyle because it's very easy, but you can just use Desmos for that. So here's the graph. I used the Desmos quickly and just got that, but the reason I punch in this is the graph y equal to x plus 2. You can actually do it freestyle, but what I wanted to actually talk about is the point of discontinuity, and it's easier to me for me to do it here. So x equals to 2 and y equals to 4. This coordinate right there, that is the 2, 4. That cannot be on the graph. So it's actually, this line has a hole on it. That means that everything past 2, so all values that are greater than, for x, greater than 2, that's part of it. And then this part here is all values that are less than 2. But 2, 4 is not part of it. And we call that a point of discontinuity. And that is part of exactly what we were talking about here. So that's the 4th case, okay? So if you end up getting a rational function where you can actually simplify, then that's what you will end up getting. And sometimes you have one, sometimes you have more, and then you go ahead and graph, okay? And that's basically it.